Hello and welcome to lecture number 19 of the course Robot Motion Planning. In the last class, we looked at systems which are subjected to kinematic constraints. That is like a car which cannot move sideways because it is subjected to the non-holonomic velocity constraint. And then we moved on to multifinger robot hands. That is when a multifinger robot hand grasps an object, then what are the constraints that are imposed by the fingertip contact onto the object surface, right? So we have seen that depending on the kind of the contact condition, whether it is with friction, without friction, whether it is soft finger contact, that will impose kinematic constraints on the object itself. Today we'll move on from there and see that if you want to manipulate an object by a multi-finger hand, say for example I have an object like this, a mobile phone, and I catch it with 3 fingers, so 2 fingers this side, 1 finger this side, and I want to do like this. Okay, so I'm going to impart a velocity or trajectory to this object, and to get this object to follow this path, what is the corresponding forces that I must apply from by my fingertips. Okay, so that is what we'll be looking at in terms of the grasp matrix. So let's start off from there, and let's very briefly revise what we had done in the last class regarding fingertip contact conditions, and then we'll move on to the grasp matrix. Okay, so we were looking at motion planning with multi-finger robot hands, and I'll very quickly revise, and then we'll move on to deriving the grasp matrix, and also looking at conditions of what are internal forces and what mathematically is the meaning of grasping an object. Now, we had seen that multi-finger robot hands are basically used for dexterous manipulation. That means when you're catching an object and rotating the object or manipulating the object, you're imparting a particular trajectory. You're expecting that the grasped object is going to follow a particular path. Okay, so we saw that there are different kinds of robot hands. So there can be 3-fingered robot hand, which is called the Salisbury hand. So it has 3 degrees of freedom on each finger, and in total it has 9 degrees of freedom, and it is actuated by wire this cable kind of drives. Now as we see further, the other kind of hand is the Barrett hand. Again, it has 3 fingers and 9 degrees of freedom. Then we move on and we see that if you want to manipulate an object, for example, I have an object like this. I'm holding this cube by a 3-finger hand. There are 2 fingers on this side, and there is 1 finger on the other side, and I want to manipulate this object. I want to translate it or to rotate it about an axis. In that case, the first thing that we need to see is what is the contact condition. For example, the fingertip is making contact with the object at this point here. So depending on the contact condition, certain constraints will be imposed on the object now. Okay, so to analyze that, we basically look at what is called screw theory, and we talk about twists and wrenches. So if you look at this 2-finger robot hand, on the right hand side, this finger is not making contact, right, with the object. Now the moment the finger makes contact with the object, there is a constraint on the motion of the object. Okay, so if the object is not moving, once the contact has been made, for example on the left hand side, you can apply a force, but you will not be able to control the velocity, right? So it's like saying that once you have an object, once you have a wall, you're pressing against the wall, you can control the force that you're applying on the wall, but you cannot control the velocity in that direction anymore. Okay, why? Because you are constrained there now. Now these constraints would depend on the type of contact that is being made. So what we see here is that when no contact has been made here, the fingertip is free to move, like in this case. Okay, it is free to move. Then we can talk about the linear and the angular velocities about an axis, and these are called twists. So this finger, which is free, it can apply a linear velocity, or it can have a moment about a particular axis at the fingertip. Now when contact has been made, like in the case in the left hand side here where contact has been made, in this case we can apply a force and we can apply a moment, okay, which are called wrenches. So wrenches are the forces and moments acting about an axis when contact has been made. Okay. So by definition, a twist is a combination of translation and rotational velocity of the object at the fingertip, okay, which is given by a linear velocity. There are 3 components and 3 angular velocities. Now a wrench is a combination of the force and moment applied to the object by the fingertip. Now there are 3 forces, Fx, Fy, Fz, and 3 moments, Mx, My, and Mz. Okay. Now in order to grasp an object, what does this mathematically mean? That is something which we'll look at today. Okay. Now we have seen that the space of the wrenches applied to the object has 6 dimensions, that is in 3D. So there are 3 forces and 3 moments, and in 2D it has 2 forces and 1 moment. Now, depending on the kind of contact that is made, different constraints will be put. Now, twists, remember, are to do with angular velocities and rotational velocities. Okay, so angular velocities and linear velocities, whereas wrenches has to do with forces and moments. Okay, and there are 3 forces, 3 moments, whereas here there are 3 angular velocities, 3 linear velocities. Now, if there is no contact, then we have seen that you can apply, it can move in any direction. For example, I have a fingertip here, which is not in contact with any object. In that case, this fingertip can move in any direction, right? So there can be 3 linear velocities and 3 angular velocities. So there are 6 twists which are possible because there is no contact. Now, because there is no contact, you cannot apply a force. So please note that you can apply only a force if there is an equal and opposite reaction as per Newton's third law, which means that you can apply a force only if there is contact. Okay, so in this case there is no contact, and hence no force can be applied, and hence the wrench is 0. Now, if we have point contact with friction, for example, this is a point contact. If you can imagine this to be a robot finger. Okay, now at the fingertip, if there is friction, then what is going to happen is that it will constrain direction. It will constrain motion in one direction. Okay, now in this particular case, there is point contact without friction. Now, if there is no friction, then the fingertip is free to move in this direction, okay, but it is only constrained to move in that direction you cannot move anymore. Okay, and it can twist about this axis, that axis, and that axis. So please note, it is point contact. It's like you have an object like this and there is a point contact being made. This can rotate like this, and it can rotate like this, it can rotate like that. Okay, and it can apply force in only one direction. So we can have only one wrench which is about the z-axis. So this is my z-axis, fx. It can apply force only in one direction, sorry, this is fz, and it cannot apply forces or moments in any other direction. In terms of twists, it has 5 twists. Okay, so it cannot move in the z direction. So that T6 which we have seen, that is not there, that is equal to 0. Okay, the T6 that was here, that one has become equal to 0 in this case, and the remaining 5 are there. So it has 3 angular velocities and 2 linear velocities. Okay. So this is point contact with friction. Now this is a kinematic constraint. That means when this fingertip is making contact with the object, it is subjected to that kinematic constraint, which has to be satisfied always. The most commonly used in case of robotic grasping is point contact with friction. So in this case, there is point contact and there is friction at the fingertip. So what will happen is it cannot rotate because there is friction. So what would happen is in terms of linear velocities, it cannot move in this direction. There is friction, so it cannot move in that direction. It cannot also move in that direction. So if you can imagine here, if you have a surface like this and I have point contact like this with friction, there is mu. Okay, what will happen is it cannot move in this direction. It is constrained. It cannot move in this direction or in that direction if this is my x, y, and z. Why? Because there is a mu into there's a mu f. Okay, so the force of friction, if this is my f is equal to mu n. So there is a mu n reaction, normal reaction on the other side. Okay, so this would basically mean that it is constrained to move because of friction. It cannot move in this direction, or that direction, but it can rotate about this axis, this axis, and this axis. So only the rotational degrees of freedom are still left, and there are 3, and the forces are all constrained. So this is my force, this is fx, fy, and fz. Okay, so there are 3 twists and 3 moments here. Now if you have a soft finger contact, which is similar to the human finger contact, so if you can imagine that if this is a hard surface and you're pressing with your finger, it will deform at the fingertip a little bit. Okay, now this is my axis, x, y, and z. Okay, in that case what happens is, so soft finger contact also has friction. Okay, so what will happen is one more additional degree of freedom will be gone. That is, you will not be able to rotate it about that axis. In case of point contact, rotation is still possible, whereas in the soft finger contact, that rotation about the z-axis is not possible anymore, but this rotation is possible. So you only have 2 twists which are left. And in terms of forces, we have 3 forces and 1 moment. Okay, so this is my moment about z-axis, and these are 3 forces. Okay, so fx, fy, and fz, and this is my mz. So you will always find that the total of this plus this is equal to 6. Okay, it just depends on the kinematic constraint that is there. Now we were talking about complete restraint and internal forces. Now what is force closure? Force closure is, suppose you're holding an object using a 3-point contact with friction. Okay, and if the rank of the matrix of the screw coordinate is 6, then it would appear that the object can resist all kind of disturbances that are going to come in the body, but that is not so. So in this particular case, it can only resist a subset of disturbances acting on the body. What it means is that you can see this very clearly from this figure on the left and the right. So on this figure on the right hand side, if I put a force in this direction, let's call this a disturbance force, the object will still be grasped. That means now what do I mean by grasp here? So what I mean here is that there will be no breakage of contact there. Okay, the moment the contact is lost, the object is not grasped anymore. So in this particular case, because the force is pushing in this direction, what will happen is the object will still be grasped. So it is stable in that sense. If I put a force in this direction now, F here, this is or my disturbance force D, then what will happen? Immediately this will come out. Okay, this contact will break. Okay, that means this type of a grasp with 3-finger with point contact can only resist a subset of disturbances acting on the body. Which kind of disturbances? The kind of disturbance which is tending to force the body into the fingertips. Okay, but the one which are going in the other direction, it will immediately destabilize it. So this is basically what we call by force closure. So force closure, when we say a grasp is under force closure, basically we mean that the object is being held by the fingers and it can resist only a small subset of disturbances acting on the object, not all disturbances. Okay, why does this happen? Because when we're talking about forces, please remember in the previous case when we talked about forces here, we talked about wrenches. Okay, the force has direction. Okay, so we have force acting in this direction. So fingertip is acting in this direction. So this is my fingertip. That's my fingertip. It's applying a force F. It can apply a force in this direction, but it cannot apply a force in that direction. It's like pulling the object. It can't pull the object, right? So there is what we call the unisense of direction. That means when we are saying the forces that a fingertip is applying a force, it is only unisense force. So fingertip can only apply forces against the object, against or push the object. So if we have object here, it can apply in this direction, it cannot apply in this direction. Okay, so that is the meaning of unisense force, and because of that we have basically what is called force closure. So it basically means that because the fingertip cannot pull the object, if there is a force in that direction, it will not be able to resist it. Okay, now the example is given here by means of holding a cube. So suppose if I have a cube like this, you might have experienced this yourself, that if there is a cube like this, I have 3 line contacts and I'm holding it like this. Okay, so I'm holding this cube this way. Okay, and if I press it in this direction, it is still stable, but the moment I press it from this side, if I give a force from this side, it will immediately destabilize. Okay, this is because of this unisense of forces, unisense of force directions, which means that the force can push but it cannot pull. Okay. And this term was first used by Renault in 1963 in France, when he talked about force closure of grasps. Now, what would be more interesting is that we are interested in holding the object in such a way that it is stable against all disturbances, that any disturbance can come from any direction but it will not destabilize. And such kind of closures are called form closure. Okay, it was basically formed by Lakshmi Narayan in 1978. Okay, and he basically said that if you have a cube, for example, he basically proved that if you have a cube like this and you want to hold it, in fact any shape, then you need 7-point contacts without friction. Then if you have contacts like this, then you need 7-point contacts without friction to hold an object in form closure. Now what is the definition of form closure? So the definition of form closure is if the collection of wrenches or forces, moments being applied by the fingertips acting on the object can resist arbitrary disturbances or all disturbances can be rejected. Okay, in such a case we say it is under form closure. And he proved that 7-point contact without friction are required to form closure of a 3D object. and 4-point contacts are required in case of 2D object. So 7-point contacts for 3D object and 4-point contacts for 2D object. Now let's look at this example, which is interesting and easy to understand. So we have a cube. This is 2D, just to understand. Now we need 4-point contacts, right? Now why 4? It's very easy. So suppose I have 3 fingers like this. Okay, there is no friction. Mu is equal to 0. Now this can be informed force closure. It can resist forces in which direction? It can resist forces in this direction. Okay, but the moment I give a force in this direction, it will immediately destabilize. Okay, it will come off. Okay, why? Because there is no friction force, so it cannot resist that force. So for doing that, I need to add one more finger. So 3 finger is not possible. I need to add one more finger. So this is my 1, 2, 3, 4. Now it is stable in all directions. Now you can push in any direction you want. Okay, the grasp will not come off. This is very easy way of understanding why you need 4 contacts. Okay. Now when we're talking about 4 contacts, the other context that comes up is where are you going to place your contacts? Okay, so I just put the fingertips in the center. Suppose I have a cube again like this. What is the best place and the most stable place to have contact to place the fingers? That is an interesting question which we'll see subsequently. So I can place it in the center like this, or I can place it in the corners. Okay. Now if I place it in the corner, what is the advantage? The advantage is that it can resist the highest moment. What is the moment acting on the center? The moment is this force into this distance, x. F into x is the moment. Okay. So if my x is large, then you require very low force in order to catch an object against a moment. Okay. So this grasp might be better than this grasp. So we see that the first thing is the number of fingers. The second thing that we have to worry about is where to place the fingers. Now, apart from that, we need to see that if I want to move this object now in a particular way, suppose I want to move the object this side, okay, in that way, then the fingertips have to impart velocities to the object, okay, and basically it has to grasp the object, that means apply force, and also move it in a particular direction with some velocity and acceleration. This I can say is the path of the object that I want to take it to. So one of the objectives of multi-finger hand is to grasp, that is to hold an object. Number 2 is also to manipulate an object. Now what is meaning of manipulating an object? It basically means moving the object in a desired trajectory or along a desired path. So I have to figure out what are the fingertip forces that are to be applied if I want to move the object in a particular path. And that is something which we'll be seeing subsequently. Now, in order to understand the concept of internal forces, let us look at a two-finger grasp having point contact with friction, holding constraining an object. This is in 2D. Okay, just to understand the concept of internal force. So we have an object here. This is in 2D. Okay, I have one force act, one finger, 2 fingers with friction. So there is a force there, force here, force here. Okay, so these are 2 fingers having point contact with friction, constraining an object. Now, what are the forces which can act on this object? Disturbance forces. If this is my x-axis, y-axis, there can be a moment about the z-axis. Okay, so in 2D, we can have two forces. So Fx, Fy, and Mz acting. Fx, Fy, and Mz. It is in 2D. So there can be forces in the x direction, y direction, and there can be a moment about the z-axis. Okay, this is in 2D. So at most, the disturbance forces acting in the CG of the object can be Fx, Fy, and Mz. That means to balance this Fx, Fy, Mz, I'm going to apply fingertip forces, which is Fx1, Fx2, Fy1, and Fy2. Now these are forces along the x-axis and the y-axis. Okay. Now from static force balance, equations, we know that sigma F must be equal to 0 and sigma M must be equal to 0 for this to be in static equilibrium. Okay. So for this system to be in static equilibrium, which is subjected to two forces Fx, Fy, and Mz in the center, we are applying 2 fingertips forces, 2 fingertips which are applying these forces. Now I need to find what is Fx and Fy in order to balance a particular Fx, capital F, capital Y, and capital Z acting in the center. Okay, so first thing what I do is I say sigma Fx is equal to 0, then I say sigma Fy is equal to 0, and then sigma mz equal to 0. So this means forces in the x direction are all equal to 0. So what are the forces in the x direction? Fx1 plus Fx2 is equal to capital Fz. Okay, that you can see from here. Similarly, Fy1 plus Fy2 is equal to Fz Fy. And if I say this distance is equal to 1 unit, then the Fy2 into 1 plus Fy1 minus Fy1, or rather Fy1 minus Fy2. Fy1 into 1 minus Fy2 into 1 must be equal to mz. So there are three equations here. Okay, one in the x direction, y direction, z direction. And if I write in matrix form, then I can write Fx, Fy, and mz is equal to 1 0 1 0 0 1 0 1 0 0 1 0 minus 1. This is the fingertip forces on this side. Fx1, Fy1, Fx2, Fy2. So this set of equations I've written there. Okay, there are three equations. So on the left hand side, I have the forces which are acting disturbance forces. These disturbance forces also consider the mass of the weight of the object. Okay. So in 2D at most you can have Fx, Fy, and Mz as disturbance. So there are two forces, one moment. Now this is equal to this matrix into the fingertip forces Fx1, Fy1, and Fz. Okay, so I hope you understand this equation, right? So I will go on from here and explain the concept of null space. So Fx, Fy, and Mz, I'll just write it again, which is equal to 1 0 1 0 0 1 0 1 0 1 0 minus 1. And here it is Fx, Fy, Fx, Fy, 2 2. Now if I write it in short form, then F is equal to this matrix. Okay, and let's call this matrix C into fingertip forces small x. Okay, let me write it this way. So what is required? Now to grasp an object, to grasp and manipulate an object, we need to apply and control the small x, small f's. Okay, that means I need to control Fx1, Fy1, Fx2, Fy2 in order to get in order to balance these external forces or to move the object in some direction. So basically I need to know what is small f, okay, for a given capital F's. So that means in this equation what I need is f, and f is equal, small f is equal to C inverse into capital F. That's what I need. Suppose I just ask this question here. We have an object. This object has weight, has mg equal to 5 kg. This object weighs 5 kg. How much fingertip force are you required to grasp this object? Okay, how would you solve that problem? So essentially we have to write our equations of statics, okay, of static equilibrium, then try and solve what will be Fx1, Fx2, Fy1, Fy2. Okay, that's how we're going to solve it. Now if you just look at this problem, please think about it. Do we have an object mg is equal to 5 units, whatever is the units. I'm asking you what is Fx1 and Fx2, Fy1, Fy2, and Fy1. If you just look at this problem, you tend to say that it is 2.5 and 2.5. Okay, is that the correct answer? Please think about it. Okay, now to solve it, basically I have to write my equation of static equilibrium like this, and what you get is these three equations, this, and this, and you actually get this set of equations. In the case when the force is acting in the there is only one mg acting in the y direction, Fx will become equal to 0, and mz will become 0, but only Fy will be there. Okay, so in this particular case we see that we need to invert this equation. Now what am I driving at? What I am driving at is that this matrix is a non-square matrix. Please note that it is 3 by 4, which means that you cannot invert it directly. Okay, if I want to find this one, it is a non-square matrix, 3 into 4. Okay, so it basically means that what does this mean mathematically? This basically means that this problem that I just spoke about, that you have an object of some weight and I want to grasp it, and if I try to solve this equation, solve it by writing equations of static equilibrium, what we end up is this equation. And if I have to take the inverse and find f, then c is non-square. So now what do I do? Okay. So here in this case, we cannot find the exact inverse. Exact inverse does not exist. Okay. So we find the pseudo inverse. Okay. Now the solution of this equation is f is equal to c hash f plus c hash c minus I into lambda. Okay. So the solution of this equation basically is, we don't have an exact inverse because this is a non-square matrix. So what we get is a pseudo inverse, which is not an exact inverse. Okay. And so we get one part of solution plus another part of the solution. So this solution comes in two parts. We call the particular solution and the homogeneous, the particular solution and the homogeneous part. Now, why does this happen? Now, this happens because if you think a little bit, if we have matrix A into A inverse, if it is an exact inverse, then this is equal to I. That means A inverse, A into A inverse minus I is equal to 0. If A inverse is an exact inverse. Okay, so if A inverse is exact, that means A is square. Is a square matrix. Now, if A is not an exact inverse, then you have A into A hash minus I is not equal to 0. This means that, what does this mean here? Mathematically, it basically means that you have 4 unknowns and you have 3 equations. Okay, so how many solutions do you have? You can end up with infinite solutions. Okay, so this actually is one part of the solution. Okay, and this is the other part, which is basically in the null space. Okay, this is the concept of null space. So you have one part of the solution here and the other one there. Now this part of the solution is basically the null space of null space of f. Okay, and there is a constant here, which is, and there is a constant there, a positive constant there. Okay, so which means that your solution now of f consists of two parts. One part is this part, and the other part is that one. Again, there is a constant there. So what it basically means is that you have multiple solutions here. How many? Infinite. So you have one basic solution, and then there are multiples of those solutions. Now please think about it. So I just talked about catching this object which is having mg equal to 5, and you said that the force, what forces are required? Fx1 and Fx2. Just by thinking, you tend to say that Fy is equal to 2.5. Okay. That is the basic solution. And there are multiple solutions which are multiples of the other fellow which is here. That is my multiple solution which is coming from here. Okay. So the other solution is basically coming from the null space, which is getting multiplied by lambda, which is a positive constant. So you can get multiple or infinite solutions. That means, what is the answer to this question that I asked? You have an object of weight 5 kg, you want to lift it. How much force is required? Okay, you tend to say half of the weight. Okay, but that is only one solution. Okay, you have infinite solutions. Any solution which is 2.5 plus this is a solution. Okay, now why did this happen? This happened essentially because this matrix here is a non-square matrix. So please think about it. Okay, now whenever you have number of variables more than the number of equations, you end up with this kind of situation. And if your matrix is non-square, then you end up with a pseudo matrix, and with a pseudo matrix you end up with a null space. A solution will consist of two parts: homogeneous solution plus particular integral, a particular solution, and which basically means that you can have one basic solution and multiples of that. Okay, now this makes sense in the real world. Why? Because otherwise, if you have to lift an object of 5 kg and you have exactly 2.5, if you apply a little bit more, it's not right, because exact. So there is nothing like exact in the real world. Okay, so if I apply any force which is more than this, it's fine. Okay, So this is the meaning of the maths part here. But what's more interesting here, or more confusing rather at times, if I write this equation again, okay, let me write this equation again, fx, fy, mz, and this is equal to 1 0 1 0 0 1 0 1 0 1 0 minus 1, and this is fx 1 fy1 fx2 fy2, and in total we said f is equal to c into small f. Okay, now suppose we have a situation in which, and the solution of this, the solution of that fellow was equal to c hash f plus c hash c minus I into lambda. Now suppose a situation exists where the object has no mass. Okay, so it basically means that this matrix is equal to 0 0 0. So there is no force, the object is massless. Where, say for example, in outer space, there is no gravity, so it's weightless, it's just floating anywhere. So if you want to catch a floating object and you want to move it somewhere, do you have to apply force? I hope you understand what I'm saying here. Okay, that we have an object which is free floating object in space. That means g is equal to 0. Okay, so do you need energy? Do you need force? Force means you have to do work. Okay, do you have to expend energy to grasp or manipulate the object? Okay, this is an interesting question. How do you answer the question? You simply look at that equation, f is equal to c into f, and which says that f is equal to c star f plus c hash c minus I into lambda. So if it is massless, means f is equal to 0. That means this fellow becomes 0. Okay, but that fellow is still there. Okay, c hash c minus I into lambda is always there. This is non-zero. It cannot become 0. Why? Because c is a non-square matrix. That means even if you want to grasp an object which does not weigh anything, you still have to apply force, which is against our perception of reality. Okay, so grasping and manipulating massless object still requires force. Okay, or rather, yeah, so let's put the exclamation mark there, which is very strange. Why? Because this one never becomes equal to 0, and that is in the null space of f. Okay, now in outer space, when objects are freely floating, even then you have to do work. Even then you have to grasp an object, you have to apply force. Now that force is exactly coming from here. Okay, so please understand this. The concept of null space is very, very important here, that when you are grasping an object and you want to find the forces that are required to grasp the object and to manipulate the object, you have to deal with the null space. Why? Because the matrix involved there is a non-square matrix. So it basically means that there is a minimum force and any multiple of that is okay. Now this would also mean that the solution of this equation here, okay, would consist of two parts, this part and this part. Okay, now let's look at what the null space would look like. So let's look at this example. Let's look at this example before we move on here. The previous example that we looked at. So we had fx1, fx2, fy2, fy1, and we had the forces acting there. So fx, fy, and mz. Okay. Now in this particular case, what will be the forces in the null space? Can we guess that? Say for example here, suppose this is equal to 0, fx, fy, mz is equal to 0. Okay, so what will be this part? Okay, can you guess? Okay, so this is the definition of grasp. What is the definition of grasp? The definition of grasp means that there must be forces in the null space, or there must always be positive forces in null space to maintain grasp. So even if this part becomes equal to 0, let me go back here. So even if this part were to become equal to 0, then also this part will be there. Now in this particular example, what will be the forces in the null space? Can you guess? So simply by looking at this figure here, if Fy is equal to 0, that's fine, it will still hold. Okay, that means Fx and Fy must always be, sorry, Fx1 and Fx2 must always be there, and they will be equal and opposite. Otherwise the graphs cannot be maintained. So in order to hold this object, Fx1 and Fx2 must be positive. Okay, it cannot be non-zero. It has to be non-zero. The moment it becomes 0, the grasp will fail. So what is, when we are saying grasping an object, that is English language. Mathematically, what is grasping an object? Grasping an object essentially means that you must have forces in the null space, and they must be positive. Okay, the moment they become 0, your grasp will fail. Okay, so in this particular case, what will be this part, if you can guess? Okay, so even if this becomes equal to 0, this fellow will be there, which means Fx1 must be equal to Fx2. Okay, so my vector is going to be 1 0 1 0. That is the force in my null space. So this is called the orthonormal basis. Okay, so the orthonormal basis is 1 0 1 0 here now. Okay, that means even if you do not have any force here, you still require this fellow to hold the grasp. Okay, so if you think a little bit on this, if I want to grasp an object and move it along somewhere, along that direction now. Okay, so I have grasped an object, this is grasped, and I want to move it like that now. So to move it, you need to apply forces, and to grasp it, you need to have internal forces. So the total force will be the forces for causing motion plus internal forces. Okay, so this is basically saying that you need to grasp the object and then move it along in some direction. So you need components of two forces now. Now let's look at just look at an example here. So this is an object constrained by one point contact with friction and one soft finger contact. How do we solve such problems? So this is an object which is constrained by one point contact. Okay, let's say two fingers, in which there is 1 point contact here. So there is 1 point contact with friction. So there is mu, and there is one soft finger contact now. Okay, what are the constraints that are there? What are the twists and the what are the wrenches that are being applied? So point contact with friction, you can apply three forces, right? So there is W1, W4, and W3. Okay, this is my x-axis, y-axis. Now, if there is soft finger contact, okay, so here there is three wrenches, okay, or three forces. Here there is 3 force plus 1 moment. So this is soft finger contact. So this is applying 3 forces, W5, W6, W2, and there is 1 moment, WM. Now in this case, this is my x-axis, y-axis. Now we simply, in order to solve this problem, we simply do Fx equal to 0 and sigma m equal to 0 and write our equations. Okay, that means I'm going to write forces in the x direction equal to 0. So this is my Fx. We are calling this W here. So W1, W2, W3, W4, 5, W6, and W7. Okay, and on this side we have Fx, Fy, Fz, Mx, My, Mz. This is in 3D. This is a 3D problem. Okay. Now when I write my equation sigma Fx equal to 0, what do I get? Forces in the x direction equal to 0. What are the forces in the x direction? W1, which is here, and W2. So W1 minus W2 is equal to Fx. So I'm writing it in matrix form. Similarly, in the y direction, what is there? So W3 is there, which I'm having here, and W5 is there. Okay. So that is how I get this matrix. Now again, note here that this is a non-square matrix. So it is 6 by 7 matrix. This is non-square. So if I want to find the fingertip forces, again I have to find the pseudo inverse and then find the null space of the matrix. Now in this particular case, what will be the internal forces in the null space? Okay. So internal forces in the null space would mean that in order for this grasp not to fail, this force must always be there and this force must always be there. Other forces can go, but those two fellows have to be there, W1 and W2. So it basically means that the internal forces in the null space will be 1, 1, 0, 0, 0, 0. Okay. Now, so this means now internal forces are always positive. The graphs can be maintained against any arbitrary disturbance. Okay. This means that when we say mathematically that the object has been grasped, we mean that the internal forces are there and they are positive. That is the meaning of a grasp being there. Now, if we think a little bit more, there can be different kinds of contacts. Say, for example, here, where you have two soft finger contacts. Okay, this is just an example. If you think a little bit, it will become clear. Now, in this two soft finger contacts, two soft finger means 3 forces plus 1 moment. So in this case, there are 3 forces, 1 moment on each side. So 3 force, 1 moment. Exactly the same way, we write our equation, F is equal to W into F. Okay, and we get this matrix, in which case this is how this is 8 by 6 non-square again. Now in this particular case, what are the forces in the internal space? Okay, what are the internal forces? In this particular case, we need this fellow, we need this fellow, we need Wm, and we need W8 also. So this is one orthonormal basis vector, this is another one. So these are called the orthonormal basis vectors. Okay, and we have lambda 1 and lambda 2, which are positive constants. That means any multiple of this is fine. So there is a one basic solution, and multiples of that solution are all correct. So when we talked about multi-fingered hands, we basically have to worry about this case where we have fingers. We have the fingers which are holding the objects, which have positive internal forces and whatever additional forces are required to move the object. So next, let's look at the grip transform for object manipulation. As I said that I have let's say this is an object, and this object is held by multi-fingered hands. Now we have one here, multiple fingers. Let's say there are 3 fingers. Okay, so this is my robot hand. Okay, this is my robot hand, and this is 3 fingers. Now this doesn't look very good. Let's say I have one more here. Okay, this is better. Okay, so these are fingers and these are contacts. Okay, now we are saying that each of these fingertips can apply a force, which is F, twist, and a wrench, which is V. Okay, so the fingertips can apply a wrench or a twist. Now because of this multiple fingers, each of these fingers can apply a twist or a wrench. Okay, what will happen is the center of the object will have some motion. Okay, so let's say the object is moving like that. So there is a sum of forces which are acting at the CG of the object, and it has some twist. Okay, so we have a multi-fingered hand which is holding an object. I want to impart some velocity or move this object along a particular path. For example, I want to move this object along this path like that. I want to move it, or let's take it simply, I want to move it along a straight line like this. Okay, I want to move the object like that. Now the fingertips will have to apply some wrench, because of which there is going to be a resultant motion of the object, and it will go in that direction. And it basically means you have to grasp plus move. Okay, it is exactly similar to in the case of multi-agent systems. When we talk about we'll see this in the next class, where we have multiple robots, okay, multiple mobile robots which are pushing this object in some direction. This is a multi-agent system. It's exactly the same problem, where these small agents are applying forces and trying to force the object and take it in some direction. We can also talk about capture, where we have a object which is moving around, and I have multiple robots which are going to go and capture the object. Okay, so this is exactly the same. The multiple robots will apply a force on the object and constrain it, and then it can push it in some other direction. So it basically means you have to grasp the object, which means you need internal forces, and you need to move, so you need to have extra forces for motion. Now how do we solve this problem? We write the if you remember, we talked about in the case of a serial manipulator arm, if there is a force acting there, then what is the relation between the force and the torques, the joint torques? So the joint torque tau is equal to J transpose into F. What is J? J is the Jacobian in the nth frame. Okay. So similarly, this gives us a relation between the joint torques and the force at the end effector. Now the grip matrix basically gives us a relation between the fingertip forces and the forces the body center is subjected to. And if I can find that relation, then I know exactly how I can move the object in any particular direction. So we call the grip matrix to be equal to G, and I write the body center forces is equal to G minus transpose into the fingertip forces, which means that F transpose is equal to F transpose into G inverse. Okay. So G is the grip transform which relates the fingertip forces to the forces the body is subjected to at its CG. Okay. Now from here, what we see is that F is equal to, so my F is equal to G transpose into small f, right? Now, what I want to do is, we want to find the relationship in terms of velocities, that what should be the fingertip velocity that should be applied in order to have a particular object velocity. Now, how do I do that? Now, what we say is, V is the twist along each of the, at contact, right? V is at contact points. Okay. So the total power input to the system is equal to F transpose into V. F is the fingertip force. So V is the contact point's velocity and P is fingertip force. Right. Now, if we say gamma is the object velocity, then this is equal to Vx, Vy, Vz, omega x, omega y, omega z, plus there is gamma 1, gamma 2, gamma 3 up to gamma n. Now, these are what were called virtual velocities or deformations. So if the object is deforming, it is also having a velocity at the fingertip. Okay, that is what is coming from here. Now, in terms of the power at the center of the body, this is F into gamma, which is equal to F. So this is equal to Fx Vx, Fy Vy, like this, lambda 1 gamma 1, lambda 2 gamma 2, okay, in this way. Okay. So power input is Ft into V at the fingertip, and this is the power at the object. So these are the fingertip, and these are the object, and they have to be equal, right? Whatever power you're giving from the fingertip have to be conserved onto the object. So if I equate these two, then F transpose V is equal to into gamma, and we have seen that F transpose into V is equal to F transpose G inverse into gamma, that we saw F transpose into G inverse from here. Okay, so let's call this 1. So from 1 we get this, and I can cancel off F transpose from both sides. This and this will cancel. So what we do get from here is V is equal to G inverse into gamma. Okay. And so I can take gamma to be equal to G into V. So this G is what is called the grip transform, and it gives the relationship between the object velocity, which is here, and the fingertip velocity, which is there. Okay. So what will this consist of? It will consist of two parts. One is called this will consist of the null solution. Okay. And this will consist of the homogeneous part. So this is the particular solution. So this is the actual solution. Okay. Plus the null solution. So in the previous case, what will we get is the grip transform will consist of, let's take the simple example, this one. So our matrix was 1 0 1 0 0 1 0 1 0 1 0 minus 1, and my null was basically what was the null solution? It was 1 0 1 0, right? So this plus this is my G matrix. So in the G matrix, it is going to come as this fellow will come to the bottom here. That's my null space. So this will become a square matrix. Okay, now you can solve it and you can find the relation between what is the object velocity and the, so here now this is my fingertip velocity and this is my object velocity. Okay, and this is my grip matrix. Okay, so the grip matrix will ensure that the null space is there, so the grasp is maintained, and this is the one that is going to give you the motion. Okay, so this part of these will cause the motion, and the bottom of it will cause the null space, will cause the grasp. So in the previous case, we looked at the solution like this: 1 0 1 0 0 1 0 1 0 1 0 minus 1, and the last one became 1 0 1 0. Okay, so this fellow is my null space, and this fellow is the motion fellow. So whatever direction I want to move the object now, let's look at this example. So I want to move the object in this direction. So whatever velocities are required in that direction, whatever forces are required, I can get from the top part of the matrix. And to maintain the grasp, I'm going to get from my null space. So I'm getting this part plus that part. Okay, so I'm getting my internal forces from the null space, and I'm getting the extra forces for moving the object from here. And that is the basic way the grasp matrix works. Now, this is also, we looked at force closure, and we understand that for 3D, in 3D, you need 3 fingers. Okay, and that is why most of the robot hands have 3 fingers, and they basically work on the concept of force closure. Okay, so this gives us an example that if you look at various robot hands, the Stanford hand, Barrett hand, robotic hand, skunk hand, they all have 3 fingers because that ensures force closure. Now, it's very interesting to note that there has been a lot of research in terms of how would you grasp an object. That is basically called searching for force closure grasps. One way is, if you look at a regular object, this is a regular object, cube. I can slice this in terms of 2D objects. Okay, I can slice this and make it 2D. So if I slice it, it will become like this. Then I grasp it by holding it here, here, and here. Okay, so I can basically identify these points before I grasp it, and then I grasp it. Okay. So there has been a lot of research, and interesting things of research is how do you autonomously grasp an object, and people have been working for a very long time. So this is basically called search for force closure grasps. So if you have regular objects, it's not much of a problem because you can identify areas where you can grasp, and then you can go and grasp it. Now, people have looked at pre-computing grasp sets. For example, if you're given a cube, how to hold it. So this is a cube, and you're supposed to hold it. So you can go and hold it in that order. Now, there are other solutions also. These are all solutions. We have seen that in the null space, you can get multiple solutions. Okay, so these are also solutions. So the grasps can optimize a function and get into those points. The other, for a multi-finger hand, another way of looking at grasping using multi-finger hand is by generating this database of grasps. For example, if you're given an object like a hammer and you want to hold it, okay, then what they do is what is done is there is a shape matching between the hand and the object, and then an index is optimized. For example, how would you hold the object? Okay, so the best way of holding an object to satisfy a particular index. So they basically match the hand pre-shape and the index, and they try and proceed. Now, recently there has been a lot of interest in grasping and manipulation planning, that you need to grasp and then you need to manipulate the object. For example, in cluttered environments like this, okay, this humanoid robot has to pick up an object and move it somewhere without hitting something. Okay, so that means grasping and manipulation. So what is basically done is we compute metrics. One of the metrics could be compute the clearance from point to an object on nearest obstacle. Say, for example, if we want to catch this object and I want to move it somewhere, then I see what is the obstacle distance from the other obstacles and take that as a metric. Okay, then look at the clearance, look at the grasp quality in terms of where can you catch. In terms of quality, the minimum force can be 1. I can catch here, here, and here. That will give me the minimum force required. Reachability, then add all of this and put some kind of a total score and make that a metric. Okay, so these are some of the areas of research which is very active these days. People are also using machine learning, that instead of trying to solve this problem in terms of doing the mathematics and the algebra by using machine learning techniques. Now, in terms of the course, we have studied things like RRT. So people have also started using concept of RRT, the grass planning using RRT, random trees. That is, suppose you are here and you want to go here and catch an object. Okay, say for example, this is my object and I want to catch this object. So this is my object and I want to catch it using 3 fingers. So 1 finger here, 1 finger here, 1 finger here. Okay, so what we can do is by using a sampling based method, I can start from here, start shooting these nodes, make these edges, and see by placing different fingers how can I go and catch this object and optimize some metric. Okay, this is by grasping using RRT, but it is extremely difficult because there are 3 fingers. You have to place the 3 fingers such that you have to satisfy the grasp and also hold the object. But RRT type planners are also used for this kind of tasks. Now, this is the latest area of grasping manipulation, where if you are given some kind of a object which is not a regular object, okay, like a square or a rectangle, how do you go and catch it? By using a multi-finger hand. Okay, so people use RRT by manipulating or optimizing some index, and then they go and catch this object. So today we looked at multi-fingered robot hands and the basic mathematics and the algebra that is involved, the concept of null space. Because when we are talking about null space, when we are talking about grasping, mathematically it basically means that you must have forces in the null space to be positive. Then only you can have a grasp, otherwise the grasp will fail. Okay. So in terms of motion planning, grasping and then manipulating the object is basically meaning that you need to have forces for moving in a particular direction along a particular path, but at the same time you must also maintain internal forces. Okay, and that is what makes grasping and manipulation very, very difficult. Okay. Now, as of today, there is no robot in the world which can actually take a pen and do very simply like this. Okay, it looks very simple, but it's not, because of the mathematics involved. Okay, so this is something very interesting to note, and please think about it, that human beings can move the fingers and move a pen like this so easily. A robot cannot. Why? Because it can't solve those kind of equations in real time, and it does not have sensors. So there is no way by which it can actually measure the force and apply that force in particular sequence to get this kind of motion. Okay, so today we'll stop here today, and in the next class we'll move on to the next topic, that is optimization in motion planning. That when you have multiple agents, so you have multiple fingers, multiple robots doing a task, how are you going to use optimization to get your path results? So we stop today. Thank you.